Chapter 3, Measure the Center Variation. And in this section, we're going to concentrate on z-score and percentile, quartile, also as a box plot. So first one, let's look at the z-score and then percentile, quartiles. So all those terms are used to measure the relative standing of the data values. And again, those z-score, percentile, quartile are used to compare the values from different data sets. Or you can use them to compare the data values from the same data set. The most important concept is z-score. We're also going to talk about percentile and quartile, and also the graphical representation of the file number summary. We call that the box plot. It's also a graph. Box plot is a graph. So let's get to the basic of the z-score, percentile, quartiles, and box plots. So z-score is a standardized value. Measures how many number of standard deviation that is given data value x is above or below the mean. So for example, on the bell curve, the mean is right in the middle. So you just basically compare the data values to the mean, right? Okay. And we use this number of standard deviation above or below the mean to capture the relative standing of the given data value x. So I have two formulas to calculate z-score. For the sample z-score equals sample mean, data value minus sample mean, x bar represents the sample mean, and then s represents the sample standard deviation. So data value minus sample mean over sample standard deviation for the sample. For the population, using the data value minus population mean mu. So mu represents the population mean, and then sigma represents the population standard deviation. Okay, and find the quotient of those, you get a z-score for the population. All right, so always run the z-score to 2 decimal places. It's like a convention. Okay. You'll see why we do that in chapter 6. Okay, so now let's try to interpret the z-score. So right in the middle, the z-score equals 0. So in this particular range between 2 standard deviation below the mean and 2 standard deviation above the mean, we call these ordinary values. So ordinary values occurs when z-score is between greater equal -2, less equal to 2. And anything beyond the range will become unusual values. Okay. So here this z-score is greater equal -2 and 2. On this particular range, that unusual value occurs when z-score is greater equal to 2, or z-score is less equal to -2. Okay. So unusual values occur, z-score is less than -2, z-score is greater than 2. So I should erase that equal sign here. Okay. And let's take a look at an example about calculating z-score. So the author of the text measured his pulse rate to be 48 beats per minute. We can assume this is x value, x equal to 48. Okay. And here is the pulse rate unusual if the average adult male pulse rate is 67.3 beats per minute. You can assume this is a sample, then this is going to be the sample mean. Sample mean equal to 67.3 beats. Okay. And we also have a sample standard deviation of s equal to 10.3. And now we just apply in the z-score formula, z-score equal to x data value minus sample mean over the sample standard deviation. So you have 48 minus 67.3 over 10.3. Let's see what that is. 48 minus 67.3. And dividing by 10.3. It turned out to be negative 1.87 approximately. Negative 19.3 over 10.3 approximately equal negative 1.87. So again, if you look at this z-score, it's right in the middle of negative 2 and 2. So this z-score here is that's greater equal negative 2, less equal to 2. That means this pulse rate is usual, right? It's not unusual, meaning it's usual. So using the z-score, we could be able to identify those usual values, also the unusual values. Now let's move on to percentile. So this percentile concept is basically dividing the entire data set into 100 equal parts. Entire data set into 100 equal group. So each group occupies 1%. So on that 99 percentile denoted, so using this P1 represent percentile 1, P1. P2 represent percentile 2. P99 represent percentile 99. Okay, so you divide the entire data set into 100 equal groups with about 1% of data values in each group. Okay. And P represent percentile, the subscript number represent the percentile number. Okay. Now, in order to find the percentile of data value, you basically just measure number of data values less than x, less than the given data values, over total number of data values times 100. So for example, if you look at this, we're still using the same example, 40 cookies, find the percentile of cookie 23. So 23 is right here. This is 23, the first 23. If you look at it, about 10 numbers below 23, you can count it. Okay. Each row has 10 numbers. So the percentile of data value 23. Number of data available below 23 is 10. Over total data values, in this case is 40. 10 over 40 times 100. That becomes 1,000 over 40 becomes 25. This means the cookie with 23 chips is ranked 25th percentile in the data set. So cookie with 23 chips is percentile 25. Okay. All right, that's how you capture the percentile of any data values here in the data set. And sometimes we may have to go backwards. We may know the percentile of the data values, but we want to go back to the corresponding data values. So select the inverse process. Now you know the percentile, then you want to go back to the corresponding data value. So here we use this formula. L means locator. L here is locator, give us the position of the data value. K is the percentile we're talking about, percentile being used. N is the total number of data values in the data set. You can also say the sample size. And the P of K represents kth percentile. as we explained in the earlier slide. So locator equal to n times k over 100. Now, once you have the locator, first of all, we sort data, arrange the data in the increasing order. Then we use a locator formula to calculate the locator, n times k over 100. And now, if locator is whole number, yes, if it is whole number, then you're gonna average the lth data value and the next value. So lth plus lth data value plus lth plus 1 data value and divide by 2. If the locator is a whole number, okay, so this is where the data value is located. Okay, data value will be calculated using this. If L is not a whole number, then you always run it up to next whole number. Okay, so that means it will be L plus 1. Data value is what we're looking for. Okay, so this is two like rules you have to follow in order to locate the data value. So now let's take a look at quartile. So quartile, we have a quartile 1, still is the measure of the relative standing. So we have quartile 1, quartile 2, and then quartile 3. So basically, you quartile 1, quartile 2, quartile 3 divide the entire data set into 4 groups with about 25% of the data values in each group. So quartile 1 is the same thing as percentile 25. So this is what we call the first quartile. It separates the bottom 25% from the top 75%. And quartile 2 is the same thing as median. Separates the bottom 50% from the top 50%. Because median is the middle. So quartile 2 is the middle number. Quartile 3 is the same thing as percentile 50. Okay. Quartile 3 is the same thing as percentile 75. So we also call this third quartile, separates the bottom 75% from the top 25%. Okay. So now visually speaking, you can look at it as this. So quartile 1 here is located right here. So bottom 25% from top 75%. Quartile 2 is right in the middle, separates the bottom 50% from top 50%. Quartile 3 separates the bottom 75% from top 25%. So this is what we call the 5 numbers summary. So here we have a minimum, quartile 1, quartile 2, quartile 3, and a maximum. So we're using those 5 numbers to summarize the entire data set. Okay. We also have other important statistics we use to measure the relative standing here. We call this interquartile range, IQR, equal quartile 3 minus quartile 1. Semi-interquartile range, quartile 3 minus quartile 1 divided by 2. Mid-quartile range is quartile 3 plus quartile 1 divided by 2. 10 to 90 percentile range, percentile 90 minus percentile 10. Now the 5 number summary already listed in the earlier slide. So we need to find those 5 numbers, minimum values, first quartile, quartile 1, percentile 25, second quartile, quartile 2, same thing as median, next to the third quartile, quartile 3 is percentile 75, and then also the maximum values. And the box plot is basically the visual representation of the 5 number summary. Visual representation of 5 number summary. 5 number summary. We also longer version of names, box and risk diagram is a graph of data set that consists of a line extending from the minimum value to the maximum value, and then the box with the lines drawing through the first quartile, median, quartile 2, and also the third quartile, quartile 3. So we put a quartile 1, quartile 2, quartile 3 right in the box. So in order to construct the box plot, we start with a 5-number summary. So find those 5 numbers first. Then after that, second step, construct a scale with the values includes minimum and maximum data values. And then we create a box, rectangle box, extending from quartile 1 to quartile 3, and draw a line in the box at the value of the quartile 2. Now after that, drawing the line extending outward from the box to the minimum and maximum values. Okay, so now I'm going to show you how to construct a box plot for the above data set from the cookie examples. So now we know that in this cookie example, we have 40 data values, n equal to 40. And we need to find out the first of all, it's already sorted in increasing order, so we know the minimum value. Minimum turned out to be 19. The second one is find the quartile 1. Quartile 1 is percentile 25. So right here we know sample size is 40, k equal 25. Okay. And then we can find out the locator first, right? So locator equal to n times k over 100. So do 40 times 25 over 100. That's 1,000 over 100, turn out to be 10. So now this locator is an even number, That means we get to average the 10th data value. So the quartile 1 equal to average of the 10th data value, 10th value plus 11th value. And divide by 2. So now let's go to the table here. Let's see which one is the 10th data value. 22 is the 10th data value. 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. 23 is the 11th. Right. This is 10th. This is 11th. So you just average those two numbers. So it's going to be 22 plus 23 divided by 2. So that turned out to be 45 by 2. So it's 22.5. So the quartile 1 turned out to be quartile 1 equal to 22.5. Okay. Now we're going to move on to quartile 2. So quartile 2 is the same thing as median. That's the third number we're looking for. And you can go back to the table one more time. The median must be between the 20th, this is 20th data value, and 21st. This is 21st data value. So median is right in the middle of those two. So Q2, quartile 2 is equal to 20th data value 24, and 21st data value is also 24. Adding those two divided by 2. So this 48 by 2 is turned out to be 24 as well. So quartile 2 turned out to be 24. Now let's look at the quartile 3. Quartile 3 equal percentile 75. So now n equal 40, k equal to 75. So locator equal to n times k over 100. So it's 40 times 75 divided by 100. That's 3,000 by 100. Okay, that's 3,000 by 100. That's right. 30. Okay, again, this is 30. You can answer equal to 30. So this is still the whole number. That means percentile 75 is located between the average of the 30th data value and the 31st data value. So quartile 3 equals 30 data value plus 31st data value and divide by 2. So now again, you go back to table, and this is 30th, this is 31st. So you just add those two numbers, divide by 2. So 26 plus 26 by 2. That turned out to be 26. Okay. So quartile 3 turned out to be 26. The last one is maximum. Okay. Maximum here is equal to the largest number here, turned out to be 30. Okay. Now we have 5 number summaries. So we can list it here, 5 number summary here. First number minimum equal to 19. Second number quartile 1 equal to 23.5. Third number median quartile 2 equal to 24. Fourth number quartile 3 equal to 26. And then the last number maximum equal to 30. Okay. So we're going to use this to construct a box plot. So now this is box plot. Alright. So now the box plot starts with the minimum and maximum here. So this is the minimum. That's the maximum. If you want to put a number on top, you can do that. 19 goes here. And the maximum turned out to be at 30. So the total distance between the maximum and the minimum is 11. So now let's compare we're using quartile 1 minus minimum over maximum minus minimum. Okay. So quartile 1 is 23.5 minus 19 over the difference between the maximum and minimum is 11. So this is 4.5 over 11. Let's see what that is. And this turned out to be about approximately 41, meaning 41, right? So if you look at this, the whole entire distance between minimum and maximum is 141, meaning it occupies 41%. So it should be somewhere here. So again, if you draw it by hand, you can get a perfect graph here. So it should be somewhere around here, 41%. So you draw a box, draw a line here representing quartile 1. Okay, 40% approximately. Now similarly, you dividing quartile 2 minus minimum over maximum minus minimum. So it's going to be 24 minus 19 over 11. So it's 5 over 11. And that's 45 approximately. So that means they are very close. 45 is very close. So quartile 1 should be somewhere here. Okay. 23.5. This is 24. Okay. Now let's just locate a quartile 3. Then we're almost there. Quartile 3 minus minimum over maximum minus minimum. So this is going to be 26 minus 19 over 11. 7 over 11. Let's see what that is. 7 over 11. 64. So that would be approximately 64%. So it should be somewhere here. Now we locate a quartile 3. But first of all, we're going to make it the little box in the middle. Okay, so the middle one becomes a rectangular box, right? Now from here we extend on both ends. Okay, now we'll be able to get a box plot here. This is 26. Okay, and this is exactly how you will construct a box plot using the 5 number together with the ratio proportion to nail down the quartile 1, quartile 2, quartile 3 and put into the box. Then after you construct the box, extend it towards the maximum minimum with a line. Okay, so that's look at the typical box plot with a normal distribution. If you look at this, about 25% data here, 25% data here, 25% data here, 25% data here. So we will call this a normal distribution. Okay, so for normal distribution, there's no skewness. Okay, and this is very typically, if you draw the bell curve, it will be skew to the right. We have a very long right tails here, so that's a skew. This is a skew distribution because most of data values are concentrated on the left end. Okay, and this is about NCAA football coaches, right? And typically, only those famous coaches make a lot of money, but most of them making the average salaries. That's why we have this kind of a skew to the right distribution. Okay, meaning most of the salaries are concentrated on the low end. And then if you look at the outlier, it's a value that lies very far away from the vast majority of the data values in the data set. So here, if you look at this probably is some kind of outlier area. Only those famous coaches makes a lot of money, and those are the outliers we're talking about. Very far from the majority of the data values. So the outlier could have a dramatic impact on the mean and also the standard deviation, because when you calculate the mean and the standard deviation, you're including the outliers. Outlier has a dramatic effect on the scale of the histogram, so that the true value distribution is totally obscured. Okay, so outlier also have impact on the histogram, also the graph. So far we up to Chapter 3, we're learning context of data, source of data, sampling methods, measure of center variations, distribution, outliers, and changing pattern over the time. We also have learned some conclusion and practical implications about the data values.